And welcome back, everyone. So today we are going to start the last section that we'll be going over in Chapter 3, which is optimization problems. I'll be doing a separate video for sections 3.8 and 3.9, but they will not be on the exam. They're more kind of like odds and ends for differentiation. But this is important. Optimization problems are insanely awesome. I think you're going to enjoy them, and all the work you've done up till now with the graphing has prepared you well for what's about to come. So let's start off with the actual homework, the last set of homework that we had. And as some of y'all noticed, I said 2.5 in the video, but what I really meant was 3.5. So from 3.5, we had started off with number 20. And so we had the limit as x approaches negative infinity of 4x squared plus 5 over x squared plus 3. Now, I asked y'all to go ahead and just graph all these, so we're going to call that our f of x, and then we're going to go through the whole process. So we're going to start off. Step 1, are there any discontinuities? Absolutely not. That is always going to be positive down there. So that one's good. Then we go to step 2 for the critical numbers. And for the critical numbers, what do we need to find? Yes, f prime of x. So that's going to be the derivative of what we have above, and that is definitely going to be a quotient. So we're going to start off with the bottom. So x squared plus 3 times derivative of the top, which is just going to be 8x minus the top, untouched, 4x squared plus 5 times derivative of the bottom, which is going to be 2x. Okay? And then all of that is going to be over the bottom squared. So quantity x squared plus 3 squared. Okay, when I multiply all this out, I'm going to wind up with, see if I can get all this on here. I'm going to switch to over here so I can get a little more room. F prime of x equals, here we go. So when I distribute, I'm going to get 8x cubed plus 24x, and then minus 8x cubed minus 10x. Okay? So, and all that is over the x squared plus 3 squared. Okay? So, the 8x cubed and the negative 8x cubed canceled. They become 0. Then I'm left with 24x minus 10x, which is just 14x over x squared plus 3 quantity squared. Okay? So that is my f prime of x. And I'm just going to clear the screen and move to the next step, the next piece of the step where we do a and b on a clean slate. So here we go. We've got f prime of x is equal to 14x over that quantity, x squared plus 3 squared. Oops, paren. Alrighty, so we are looking, first off, are there any discontinuities? No, there are no discontinuities because I'm squaring something on the bottom that can never go to 0. So no worries there. That is completely continuous everywhere. So no discontinuities. And then for part B, I need to know when f prime of x equals 0. Well, that implies that that occurs when 14x equals 0 or x equals 0. So we have a horizontal slope at x equals 0. So that's good to know. So now that we've done that, we can fill out the chart. So step 3, we got my f prime chart. And so the f prime chart is going to have one location, x equals 0, and I just need to do a value that is less than 0. How about negative 1? So f prime of negative 1 is equal to, well, the bottom's always positive. If I put a negative 1 for the x up here, it's going to become a negative divided by positive, which is negative, which means the slope is going down. And then if I choose a positive value, like x equals 1, I'm going to get the opposite, because now the top is positive over the positive, which is positive, which means I have a slope going up. So that means that x equals 0 is what kind of critter? Yes, that is a minimum. Alrighty, so a lot of information already. We're moving forward. Let's go to the inflection points. How do we find the inflection points? Well, we need the second derivative, right? So f double prime of x equals, alrighty, so f prime of x is 14x over this x squared plus 3 quantity squared. It's another quotient, so we're going to do the bottom untouched, x squared plus 3 quantity squared times derivative of the top, 14, minus the top untouched, 14x, times derivative of the bottom. This is going to be a chain rule. It's a power rule that kicks in the chain rule, so it's going to be 2 times x squared plus 3 to the first power times the derivative of the interior, 2x. Alrighty, and all of that is going to be over the bottom squared, so now we're going to have x squared plus 4 to the fourth power. Alrighty, so there we have it. Now, I could distribute all this and be really sad panda because that's a lot of work, or I could recognize that there's an x squared plus 3 term here, here, and here, which means I can divide by an x squared plus 3. So I'm going to divide by x squared plus 3 to the first power every single term, so that'll lower this to a 3, it'll lower this to a 1, and it will take this whole thing and make it a 1 because we're going to be dividing x squared plus 3 over x squared plus 3, so it's going to just become a 1. Now I can multiply this through much easier, and I'm going to wind up with f double prime of x equals, let's see, 14 times x squared is 14x squared, 14x squared, and then plus 52, wait, not 52, 42, not 52. Sat there, and as soon as I did, I was like, wait, that doesn't look right. 42. Alrighty, and then over here, I'm going to get 2 times 2 is 4, 4x times negative 14x is negative 56x squared. Is that what y'all get? And then all of that is over x squared plus 4 to the third power. Okay, when I combine my like terms, I'm going to wind up with, I'll put it right here where it's kind of to the side, negative 42 x squared plus 42 over x squared. I might have to get to plus 4. Gosh, my pen is possessed tonight, I think. I think it could also be I just had an insane amount of nachos with chili cheese nachos, homemade, that to be honest, I'm probably in a brain fog from that much food. So anyways, over x squared plus 3 to the third power. Okay, so this is my f double prime of x. And so I'm going to copy that onto the next page, and we will start clean and fresh. So here we go. If I can actually clear this. So we're going to have f double prime of x is equal to negative 42x squared plus 14, or 42. See, listen to me. Oh man, I need to take a caffeine break over x squared plus 3 quantity squared. You didn't see anything. Now, that's my f double prime. Now I'm going to take a nice refocusing breath, and here we go. Are there any discontinuities? Well, no. It's still going to be something positive. Positive cubed is still positive. It can never go to 0. So this is no discontinuities are possible. But for part B, f double prime of x equals 0, well, that implies that the top is equal to 0, so negative 42 x squared plus 42 equals 0. Not too bad. I'm going to divide every term by negative 42. I'll get x squared minus 1 equals 0. So x is going to equal plus or minus 1. Those are going to be my inflection points. So I now have something to look for when I'm looking for my f double prime chart. I'm going to have 2 locations. So let me turn the page. I can actually turn the page. Alrighty. So we've got our f double prime chart. Let's see, f double prime chart. Alrighty. So going to have one location at x equals -1, another location at x equals +1. So I need a test value that is less than -1. How about -2? Of x equals -2. So f double prime of -2 equals, alrighty, well, if I plug in -2 in, the bottom's positive. So I know the bottom's positive, but what happens up top? Well, whatever I plug in here is going to wind up being positive. And in this case, it's going to be 4, positive 4 times -42 minus, plus 42. So -168, something like that. Doesn't really matter. It's a larger negative number than this is positive. So the answer is going to wind up being negative. And since it's negative, we're going to have concavity of concave down. Alrighty, now we move to a test value between -1 and 1. Alright, so x equals 2/3. No, x equals 0. Always way easier. So f double prime at 0. Well, plug a 0 in. This term goes away. I'm left with positive over positive, which is positive, which means it's concave up, which I feel happy about since the previous one was concave down. And now a value greater than 1. How about x equals +2? And f double prime of +2 is going to equal, well, it's going to be the same thing as when it was -2 because I'm squaring it. So again, it's negative, which means concave down. Okay? So not too bad. Now that I have these values, I can move on to my y values. Let's see. Let me clear this. Let me go to the y values. So step 6, the y values. Alright, we got a few to find this time. Not too bad. First off, let me write my original function up here. F of x was equal to, what was it? 4x squared plus 5 over x squared plus 3. Something like that. Alrighty. So we're going to start off with the critical number, y values. And there was only one, and it was at x equals 0, right? So at x equals 0, what do we get? Well, if I plug a 0 here, a 0 here, I'm going to get 5/3. So f of 0 is equal to 5/3, which means we're going to have a critical number at 0, 5/3. Okay? Now, I want to move to my inflection points. So the inflection points, the first one was x equals -1. And so f of -1, where is it located in the y? Well, when I put the -1 in, it's going to square, become +1, so 6 over 4. Well, not 6, sorry. 4 times 1 is 4, plus 5 is 9 over 4. This is going to equal 9 over 4. And so its location is going to be -1, 9/4. Okay? And then I had one at x equals 1. So when I look at f equals 1, I wind up with exactly the same thing because I square it. So this is also 9/4. So 1 9/4. Okay? Now, step 7, horizontal asymptotes. Here we go. Get some more practice with these. We're going to look for the ha's. So the ha's are at the limit as x approaches positive infinity. We'll look at that first, of the original function, 4x squared plus 5 over x squared plus 3. And so the way that we can simplify this is by dividing every term by the highest power x, which is x squared. So this is going to be the limit as x approaches infinity of 4x squared over x squared plus 5 over x squared over x squared over x squared plus 3 over x squared, which is going to simplify. This is going to become a 4, this is going to go to 0, this is going to be a 1, and this is going to 0. So what do I wind up with? 4 over 1, which is 4. That is going to be the end behavior as it approaches positive infinity. But what about negative infinity? Well, it won't matter because I don't have anything I need to divide it by. It cancels out here, it goes to 0 here, it's not going to affect anything. So this is 4 plus, let's see, y. I guess I could say like, that's my y value. So, and then that says x goes to plus or minus infinity. So we're going to have a horizontal asymptote at y equals 4. Okay, so let's see. What do we need to do now? I think we have all the information to sketch it, so let's sketch this thing. If I can clear the screen. So I have something that may look like this. I've got a horizontal asymptote at y equals 4. So something like that. And then I have a horizontal slope at, what was the value? 5/3, 0 5/3. So about right here, a horizontal slope. We said it was a min. And then I have 2 inflection points at, there's 1, 2, and 1, 2, 9/4. So -1, 9/4. So somewhere around here. And +1 and 9/4. Right about here as well. Which looks weird with the tip mark, but that is pretty symmetrical. And I know that it can never cross, it's not going to cross this y equals 4 horizontal asymptote, so it has to look like this. Assuming I can draw, which I absolutely cannot. Alrighty, so that's pretty much the graph, and it kind of makes sense because I knew that my concavity was going to be concave down up until x equals -1, concave up from -1 to 1, and again concave down. So this is exactly what it winds up looking like. And so, hooray, we did it. Now to move on to the next one. Clear this. Alrighty, so let's try 3.5 number 26. So 26 is, it asked me to find the limit as x approaches -infinity, but I wanted y'all to do the whole thing. So the f of x was equal to x over root x squared plus 1. Okay? Now, I'm going to do a rewrite of this as x over x squared plus 1 to the 1/2 power, just because that's going to make my differentiation a lot easier. So first off, let's start with step 1. Are there any discontinuities that would lead to vertical asymptotes? And even though this is a root and in the denominator, it will never be negative because I square whatever value I put in for x and add 1, and it will never be 0 for the same reason. So there are no discontinuities for this, no no vertical asymptotes for this whatsoever, so don't have to worry about it. Then move to step 2, the critical numbers. So for the critical numbers, I'm going to need f prime of x, and that's going to require a quotient. So here we go. It's going to be the bottom untouched, so x squared plus 1 to the 1/2 power times derivative of the top, 1, minus the top untouched, x, times derivative of the bottom. It's going to be a power rule with a chain, so 1/2 times x squared plus 1 to the -1/2 power times the derivative of the interior, 2x. And where'd that -1/2 come from? Well, 1/2 minus 1 is -1/2. So I have all of that over the bottom squared, and I'm going to leave it in fraction form. So this is going to be x squared plus 1 to the 2/2 power. Alrighty. So like with the last problem, I noticed that there's a factor that is the same in every term on the top and in the bottom. They all have an x squared plus 1 in common. And this is a fractional exponent. So I'm going to divide by a fraction. And the correct fraction to divide by in order to simplify this is going to divide every term by every term by x squared plus 1 to the negative 1/2. If I do that, this exponent here is going to become a positive 1, because positive 1/2 divided by negative 1/2, it's positive 1/2 minus negative 1/2, which is 1/2 plus 1/2, which is a 1. But now on this side, when I divide by the exact same thing, the whole thing becomes 1. And down in the bottom, I'm going to add 1/2 to it again because I'm subtracting a negative, so this becomes to the 3/2 power. Okay? So when the dust settles, I'm going to have f prime of x is equal to, I've got, this is to the first power, so it's just x squared plus 1, like that. And then over here, I'm going to wind up with 1/2 times 2x, which is just x, times x, it's just x squared. So minus x squared, and then all of that over x squared plus 1 to the 3/2 power. Okay, so when I subtract the x's, they go away, and I'm left with 1 over x squared plus 1 to the 3/2 power. Alrighty, so that is my f prime of x, which is kind of nice. And so I can go straight into, what about part A? Are there any discontinuities? Nope, that will never be negative or 0. What about part B though? F prime of x equals 0 implies in this case that 1 equals 0, which means no solution, which means that my f prime chart, I can skip it because there are no critical numbers to plug in. Alrighty, not too bad. I've got my f prime of x, and now I can move into finding my inflection point. So let's clear this, and I'll do my f prime of x over here. F prime of x is equal to, it's just 1 over x squared plus 1 to the 3/2 power. Alrighty, so for step 4, I'm looking for my inflection points, and they occur when I have f double prime. Well, f double prime of x, I'm going to do a rewrite of this to make it even easier. This is just x squared plus 1 to the negative 3/2 power. So it's just a power rule. So that becomes negative 3/2 times x squared plus 1 to the negative 5/2, because I have to subtract 1, times the derivative of the interior, 2x. Now this 2x multiplies with this value, but this whole term is in the denominator. In other words, if I wrote this the way it really looks, this is negative 3 over 2, and then the 2x is on the top, and the x squared plus 1 is the 5/2 in the bottom. So this 2 is going to cancel with this 2, and I'm going to be left with, I believe, negative 3x, I sure hope that's right, over x squared plus 1 to the 5/2 power in the bottom. That is my f double prime of x. Okay, this right here. Box it in. I want to keep that. Okay, so part A, are there any discontinuities? No, there are no discontinuities, for that is continuous everywhere. What about f double prime of x equals 0? Well, that's going to imply that negative 3x equals 0, which means what? X equals 0. Okay, so now I have to move to my f prime chart. F double prime chart, rather. I've already done the f prime. So f double prime chart, I'm going to look at x equals 0. So I need test values on either side. How about negative 1? X equals negative 1. F double prime of negative 1 is going to equal, well, if I plug a negative 1 in here, the top becomes positive. The bottom is always positive regardless. So positive over positive is positive. which means it is concave up. And then a test value over here, maybe x equals positive 1, f double prime of positive 1. Well, the top will be negative then, over positive, negative, so I get concave down. Okay, so that's not too bad. Now I can go ahead and do the y values too, because there's not that much to them. I got my y values. I only have one y value to look at, and that is at x equals 0. That's an inflection point. So that's an inflection point, and it is at x equals 0. So what do I plug that into? I'll plug it into the original. So let me rewrite the original. F of x was equal to x over root x squared plus 1. And if I plug a 0 in for that, so if it's 0, top goes to 0, the bottom does not, so it's 0, which means the inflection point is located at 0, 0. Alrighty, we're getting there. Now, last step, well, not last step, but last step before we can sketch. Let me find my horizontal asymptotes. So, 7 horizontal asymptotes. Well, I've got my original function, which I still keep having to rewrite. F of x is equal to x over root x squared plus 1. Okay, so let's start off with the limit as x goes to positive infinity. Well, as it goes into positive infinity, if you remember that the root of x squared is kind of like an x, so the highest power x is just x to the first. That's what I'm going to divide every term by. So this is going to be x over x over root x squared plus 1 over x. Now the substitution I'm going to make here is since I'm going to positive infinity is going to be x equals, so this one right here is going to be x equals positive root x squared. That's what I'm going to substitute right here. So I'm going to have the limit as x goes to infinity of, I'm going to have x over root x squared plus 1 divided by, and that's a plus, even though it's like a scribble, plus, and then this x is now going to be root x squared. And we'll have a root over root. I can combine them into one big root, so this is going to be the limit as x approaches infinity of x over one big root of x squared over x squared plus 1 over x squared. Now I can apply the limit. That's just going to be a 1. That's just going to be a 1. And what happens when I plug infinity in for x? This goes to 0. So I have 1 over root 1, which is 1. That is what my horizontal asymptote is going to be as I approach infinity. Y equals 1. Okay? So I can even write that if you want. I can say as x goes to positive infinity, there's a horizontal asymptote at y equals 1. Okay? Now let's see what happens as I approach negative infinity. Limit as x approaches negative infinity. Well, for negative infinity, I can't use this substitution. I have to use x equals negative root x squared, because these values are very negative. So everything else is going to be exactly the same except for this step right here. So I'm going to have x over x divided by root x squared plus 1, but now it's going to be a negative root x squared. Okay, it's going to combine in and become limit as x approaches in negative infinity. Don't want to forget that negative sign. Of, well, I'm going to have x over, this becomes 1 root, so negative 1 root x squared over x squared plus 1 over x squared. Well, this is going to go to 1, this is going to go to 1, this is going to go to 0, 1 over root 1, which is 1, but I have a negative sign, so that means negative 1. So as x goes to negative infinity, I'm going to have a horizontal asymptote at y equals negative 1. Okay? So now I have everything I need almost. I can go ahead and start sketching, and then I'll see what I need. You probably already remember what I need, but we'll assume that I don't. We'll just kind of wing it. So here we go. Let's sketch this thing. Well, I don't have a lot of information. All I have is that I'll put that 1 and this negative 1. I have horizontal asymptotes. And at y equals 1, as I'm going this way, and at y equals negative 1, if I can sketch that, as I'm heading to negative infinity. I know that I have an inflection point right there, and I know that for my f double prime chart, I had concave up, concave down. So this thing has to look like that. Except with a little bit more curvature. My gosh, I almost drew that as a straight line. Let me try that. Do over. You didn't see anything. Want to put a little more curvature in. So there we go. That's what it looks like. There's an inflection point right here where it changes from concave up to concave down. And that's what the graph looks like. It hits a horizontal asymptote y equals 1 as it hits the positive infinity, and it heads to a horizontal asymptote of negative 1 as y goes out to negative, as x goes out to negative infinity. That's it. All right, so we are almost done with homework, so let me clear this and let's start the next one. Alrighty, so now we're going to try something a little bit different than what we've seen before. This is from 3.6. This is number 26 from 3.6. And it's kind of odd. It looks very similar. There's something different going on with it. So I've got f of x is equal to x over root x squared minus 4. This is a minus sign, and so it is going to change dramatically what the final graph is going to look like, because now we can have discontinuities. So let's go ahead and think about that. So step 1, where the discontinuities will, they're where this is either a negative value or when it's 0, right? So let's look at when it's 0. So the discontinuities at when the denominator is 0, well, that's going to imply that root x squared minus 4 equals 0, which really just implies that x squared minus 4 has to be 0, which occurs at x equals plus or minus 2. Now those values, the bottom goes to 0, but the top does not, so what are they? Exactly. These are vertical asymptotes right here. Alrighty? But there's something else to think about. Can I make this value go negative? If the value that I square here is less, when I square it, it's less than 4, it goes negative. So I'm just going to write this out, and then we'll kind of think about it when we get there. Between x equals negative 2 and x equals positive 2, all of those values you can picture, put a 0 in, it's negative, a 1 in, it's negative, a negative 1, it's negative, are imaginary, because I'm trying to take the root of a negative number. So I've got that weird behavior going on that I did not have in the other, because in the other one, the bottom, the denominator was always going to be positive. There were no discontinuities because this was a plus sign. But now I've got a weird kind of looking graph, because I've got an area that between -2 and +2 that is completely undefined. Okay, so just that's something to keep in mind for the end behavior. So now I can move on just like I've done with every other one, and let's go with the critical numbers. So 2, we have the critical numbers. Okay, and that occurs when I have f prime of x. So I'm going to do a quick rewrite so I can take the derivative more easily. This is x over x squared minus 4 to the 1/2. So this is a quotient. I'm going to try to take the derivative of this, so it's going to be the bottom, which is x squared minus 4 to the 1/2 times derivative of the top, 1, minus the top times derivative of the bottom, that's going to be 1/2 x squared minus 4 to the negative 1/2 power times the derivative of the interior, 2x. We have seen this before, or something really similar, and all that over the bottom squared, which I'm going to leave in fractional form. X squared minus 4 to the 2 halves. Okay? So I'm going to do the same trick that I did before. I'm going to divide every term by what? Yep. I'm going to divide every term by x squared minus 4 to the negative 1/2 power. So when I do that, I'm going to get f prime of x equals, let's see, it will be, this one will become to the first power. This whole thing here becomes a 1, and the bottom becomes 3/2. So I'm going to wind up with x squared minus 4, and then 2x times 1/2 is x times x is x squared, so minus x squared, and all of that is going to be over x squared minus 4 to the 3/2 power. Okay, so x squares are going to cancel. I'm going to be left with negative 4 over x squared minus 4 to the 3/2 power. That is going to be my f prime equals f prime of x. Okay, so are there any discontinuities? Yep, but we already know what they are. They are all of these things that we talked about up here. That is still valid for down here. Okay, so already know those. Now what about when f prime of x equals 0? Well, in this case, that's going to imply when negative 4 equals 0, which is no solution. So there are no horizontal slopes in this function. Okay, so I'm going to squeeze in number 3 right here real quick. So what does that mean for the f prime chart? Well, we can skip it because there were no critical numbers. All right, so I can go straight to step 4, and so let me clear this and rewrite my f prime. So I have f prime of x is equal to negative 4 over, I'm going to have x squared minus 4 to the 3/2 power, which I will rewrite as negative 4 times x squared minus 4 to the negative 3/2 power. Okay, so that's just a nice easy way to look at it, because when I come down here and I want f double prime, because I'm looking at my inflection points, I want f double prime of x. So if I have this one, it's a nice easy chain rule. That becomes negative 4 times negative 3/2 times x squared minus 4 to the negative 5/2 power times the derivative of the interior, 2x. Now, this is on top, that's on top, the 3 is on top, but this and the 2 down here are all on the bottom. So if I rewrote it kind of like how it really looks, it's going to be a negative 4 times a negative 3 times 2x, and then all of that is over 2 times x squared minus 4 to the positive 5/2 power. Okay, so this 2 is going to cancel that 2, and I'm going to be left with let's see, is that 12x on top? So f double prime of x equals 12x over x squared minus 4 to the 5/2 power. There we go. That's our final f double prime of x. So, any discontinuities? Absolutely, but we already know what they are. I know that I have vertical asymptotes at x equals positive and negative 2, and everything between positive and negative 2 is imaginary. It is undefined. So now I can go to step B. F double prime of x equals 0 implies 12x equals 0, which means at x equals 0, we're going to have an inflection point, or are we? Thinkity think. Yeah, exactly. We are not, because draw this out. Just upscale. Well, that was. Thank you for drawing an imaginary line. I appreciate that. So, positive 2. This whole area is undefined because it is imaginary when I try to plug in these x values. So at x equals 0, this is undefined. I can't do anything with it. There is not an inflection point there. Even though we can solve for f double prime of x equals 0, the value that we get is in the undefined region. So, nope, can't do anything with it. So, what does this mean? It means no solution again, which means that my f double prime chart, what is that going to look like? Well, I get to skip it. There are no inflection points to plug in, so not too bad. So now I can clear this and go to the next step. So I'm going to have my y values for step 6. I think about what step I was on. So the y values, well, I need to find them for my critical numbers and my inflection points, but they were all no solution, so I can skip this too. Don't have to do anything with that. So now I can move into my horizontal asymptotes. Now this one is important because I'm going to wind up with, I need some sort of extra information. I know I've got vertical asymptotes at negative 2 and positive 2. I need some horizontal asymptotes in order to bound what I have to be able to draw. So let's go ahead and look at that. So I'm going to look at this is my original function. So my f of x was equal to x over square root x squared minus 4, right? So I'm going to look at the limit. This is for my HA. The limit as x approaches positive infinity of this. Well, it's the same as I did in the previous problem, right? I'm going to wind up with x over x, and then I'm going to divide this one, since I'm heading to positive infinity, by positive x squared, which is just going to simplify into x over x, and then I can combine these to one big root, x squared over x squared minus 4 over x squared. And when I simplify this, this is going to take the limit. That's going to be a 1. That's going to be a 1. The limit is going to make that a 0. I'm going to have 1 over root 1, which is 1 again. And exactly like before, if I look at the limit as x approaches negative infinity, I'm going to wind up with negative 1 because I'm going to do a substitution as a negative value here instead of a positive, which is going to change the positive 1 to a negative 1. So as I head out to positive infinity, I'm going to get y equals 1. As I head to negative infinity, I'm going to have a horizontal asymptote at y is equal to negative 1. Okay? So now I can sketch all this. So clear this, do a sketch. So here we go. Okay, I'll call this 1, 1, 2, 1, 2, negative 1. All right. So I know I've got vertical asymptotes at y equals negative 2 and y equals positive 2, assuming I can actually cross through the tick marks, which apparently I'm unable to do. And I know that this area between -2 and +2 is undefined. So there is nothing undefined inside of here. The graph does not exist for these x values. Okay. Now I also know I've got a horizontal asymptote at y equals 1 as I head out to positive infinity, and I've got a horizontal asymptote at y equals -1 as I head out to negative infinity. Okay, so now we've got a very similar pattern to what we've done in a previous problem. I'm either going to have something that looks like this, or I'm going to have something that looks like this. One of these two pairs. Okay. Now, the way that I solve it is all I have to do is figure out what my slope looks like, because these two always have a positive slope. These two have a negative slope. So what was my f prime equation? Well, my f prime equation was actually f prime of x equals, let's see, it was 12x, not 12x, it was -4, sorry, -4 over x squared minus 4 to the 3/2 power, right? This is always positive, this is always negative, so the slope is always going to be negative, which means the correct one is the orange. So orange is correct. Green is not what it looks like. That is not correct. So that was a positive slope. But both of these have negative slopes, so we're good to go. Alrighty, there you have it. So now we can actually move into the new content, finally. So let's knock that out. Here we go. Clear this. And let's get started. Okay. Alrighty, so let's start with the last section, which is going to be optimization problems. Okay. So what am I talking about? Well, let me start off with, let's do a graphical example. Let's say I have some function. Maybe it looks like, I don't know, that. Okay. And then I'm going to set some, I'm going to call that f. This is f of x. Okay. Maybe I'll bound it from here, a, to here, b. Doesn't really matter that much. Alrighty. And let's say I wanted to know what the minimum and maximum value between a and b on that interval for f of x is. How would I find the minimum and maximum value on this interval? Well, I'm going to look for the critical numbers where I have mins and maxes, right? So I'm looking for this location right here, this horizontal slope, and this location right here. How do I get those values? Well, to get those values, I need to find f prime of x, the derivative of my original function, and do what to it? Yep, I set it equal to 0 and solve. So if I do that, I wind up with my min and my max, or my min and my max. Okay? So optimization problems are going to be trying to find the minimum or maximum solutions for some system. And the way that you're going to do that is you're going to make equations that you then take the derivative of, set it equal to 0 and solve, and that will give you the values that will result in minimums or maximums. Okay? So it sounds like it's a lot more complicated than it is. So if it's okay with you, let's go straight to an example and see if we can get it to make sense. So let's clear this and go to let's see, for an example, let's find two positive numbers. I'm just going to abbreviate like that. Numbers whose product is 185 and whose sum is a minimum. Okay? So, what I'm going to try to do is find the minimum of the expression that will encompass. I have two numbers that are positive, that when I multiply them together, I get 185, and when I add them together, I get some minimum value. Okay? Let's take these one at a time. So I've got two things I need to think about here. I've got two positive numbers. Well, first off, two positive numbers. I'm going to make x equal to the first number, number 1, and y is going to be my second number. It's going to be number 2. Okay? So the product is 185. So that means I'm going to have x times y equals 185. Okay? And whose sum is a minimum. X plus y equals, I'm just going to put an S down for sum. Alrighty? Now, if let's say I didn't have this over here, and I came up to you and said, I'm thinking of two positive numbers whose sum is a minimum. Can you tell me what those numbers are? Good luck. Because there is no solution to that you can actually quantify. I can just say, well, I'm thinking of 0.1 and 0.01. Then I can say, okay, divide both by 10. Okay, 0.01, 0.001. Well, divide that by 10. This one does not have a solution. If I try to find two positive numbers whose sum is a minimum, there are no actual values because it's just going to be the limit as these two numbers approach 0 from the right. So, but that's not important. The main thing is, without this part, this has an infinite number of answers, or the answer is undefined because you're doing some sort of crazy limit. So I can't come up to you and just say I need two positive numbers whose sum is a minimum. But I can come up to you and say I want two positive numbers whose sum is a minimum value, but when I multiply those numbers together, I get 185. The second that I say that, I have now constrained the sum with this equation over here. So this right here, this x times y is equal to 185, has a very special term. This is called a constraint. Okay? So this is the constraint, and this is the expression that we're trying to minimize or maximize. So this is the min/max expression. So the trick is going to be to apply the constraint to this expression. Then I can actually do something with it. Okay? So how do I do that? Well, in every single case, you're going to take your constraint, solve for one of the variables in the constraint, and then plug it into your min-max expression. So you are going to, I guess if you had to do steps, write your min-max expression, and your constraint, Okay. 2 is going to be solve for 1. Solve for, I'm just going to not say 1 because we're not going to be limited to that in the future. Solve for your constraint in some way. You'll see later on if we do, and then plug the constraint into your min-max expression. All right, so let's do that. So I'm going to solve for y in this. So I'm going to draw a little box right here. Let's see, x, y equals 185. Y is equal to 185 divided by x. Okay, I'm going to take that value and plug it in to this y. Okay, so when I plug it in my min-max expression, I'm going to wind up with x plus, instead of y, I'm going to have 185 over x equals s. Now this right here has been constrained. This is my constrained min-max expression. Okay? Now, this is really nice because now I'm asking for, it's going to be kind of strange. This is kind of like in the background. I'm looking for the sum of two numbers that is going to be a minimum. Two positive numbers that are going to be a minimum when I add them together. But I know that the first number plus 185 divided by the first number is equal to that sum. That seems kind of odd. Where in the world did that come from? Well, the second number, y, is equal to the first number under 185. Y is equal to that. So this is still this expression, but now I've limited it. This expression has been constrained. When I try to solve for the minimum using this expression, I am including the constraint. So let's try that. Now I'm going to clear screen and we're going to start right with this one. So clearing this, we're going to have, let's see, it was x plus 185 over x equals s. That is my constrained min-max expression. Now I want to find the minimum. How do I find the minimum of a function? I take the derivative and set it equal to 0. Okay? So if you want to have a step 4, let's find the derivative of the constrained min-max expression, and 5 is going to be take the derivative and solve. I'm sorry, I've already taken the derivative. Hold on, let me just solve. Set equal to 0 and solve. Set derivative equal to 0 and solve. That's how you find the min or max of a function, right? I want to find the minimum of this function, so I'm going to take the derivative, set it equal to 0 and solve. So s prime is going to equal to 1 plus, well, this expression here could be rewritten as x plus 185 times x to the negative first, right? So 1, and then that's going to be a minus 185 times x to the negative second power. Okay, I can rewrite that as 1 minus 185 over x squared. So now I have my s prime. I have taken the derivative of the constrained min-max expression. Now, I set it equal to 0 and solve. So, 1 minus 185 over x squared equals 0. I'm going to move that over and get 1 equals 185 over x squared. Cross multiply, x squared equals 185, x equals root 185. Okay? Well, I just take the square root of both sides. And I know it's a positive integer, so it's the positive root. So if x is 185, how on earth do I find y? Well, I find y as, well, I've already defined that, right? Y was just 185 divided by x. So y is going to equal 185 divided by root 185. Okay? So y actually winds up equaling root 185 too. Alrighty? So back to my original problem, I want the sum to be a minimum of two numbers whose product is 185. So what is that sum? Well, I said the sum was equal to x plus y, right? So that sum is equal to root 185 plus root 185. The sum is 2 root 185. That is the actual answer. That is my sum. That is a minimum. Boom. Just like that. Alrighty. So what do you think? If I'd asked you this question, randomly, walk up to you on the street and ask you to figure that out, yeah, you can sort of figure it out once you do enough of these. You're going to notice that the square roots pop up a lot when it comes to min-max problems, for good reason. But if you didn't have experience with it, you would never guess that the minimized sum was 2 root 185. It's just not going to happen. So there you go. We just used our optimization, a little bit of calculus, to find out something that would be impossible just by thinking about it. Alrighty, so let me clear this and go to another example, a more exciting example maybe. Okay, I just looked at the time and realized I've gone over a little bit, so I'm just going to give you a quick example and a homework problem. So the next example is going to be, I have the same setup. I've got two positive numbers, and I can either, I'll just leave it like that, two positive numbers. Okay, the product is 147, and the sum, here we go, the sum of the first and 3 times the second is a min. Okay, so the sum of the first and 3 times the second is a min. Okay, what are these numbers? Well, they're going to be x and y are going to be two numbers, and x times y is going to equal 147. This is my constraint. I'm going to work this one a little bit fast since I don't want to go too far over. That's a constraint. And then I know that the sum of the first x plus 3 times the second, 3y, equals some sum, and it's supposed to be a min. So this is going to be my min-max expression. So now I need to constrain this min-max expression. I'm going to do the same thing I did before. I'm going to solve for y. So if I do that, I'm going to get, let me solve for y. X times y equals 147. Y is equal to 147 over x. Okay? So I will have x plus 3 times 147 over x equals s. Let's see, that's going to be x plus 441 over x equals s. This is my constrained min-max expression. And now I can take the derivative, set it equal to 0, and solve. So s is going to equal x plus 441 x to the negative first. S prime is going to be 1 minus 441 x to the negative second, which I know looks like s prime is equal to 1 minus 441 over x squared. So now I can set it equal to 0 and solve. That is the derivative. So I set it equal to 0, so 1 minus 441 over x squared equals 0, and I'm going to wind up with x squared, oops, let me not skip that step, I'll do it in 2. 1 is equal to 441 over x squared, cross multiply, x squared is equal to 441. What do you know? X equals 21. Okay? So, if x is 21, what is y? Well, y is 147 divided by 21. Y is 7. So, what is the minimum sum? The sum is equal to x, 21, plus 3 times y, 3 times 7, which is 42. The answer is 42. That is your minimum sum. Alrighty. Isn't that cool? That's just stunningly cool. So your homework is going to be a single problem. This is from 3.7. Try number 8. You're going to have a square there. Hold on. I'm trying to think if 8 or 9 would be good, would be better. Let's go with 8. We'll see. I honestly haven't worked number 9, but I think 8 will be okay. So just, you want to set up for number 8, set up your constraint equation, set up your min-max expression, solve for one of the variables in your constraint, plug it into your min-max to get your constrained equation. Once you have that, you take the derivative of it, set it equal to 0, and solve. Then you just find the other variable. You're good to go. Well, have fun with that, and I will see you later. Stay safe. Bye-bye.